In today's video, I'm going to show you how to simulate and extract AC losses of a superconductor with 5 filaments. First, we need to upload the step file to get the geometry. So we can see that we have those filaments surrounded by copper and then an airbox around. We can continue to define the materials. We'll need the material air for the airbox. We're going to need copper for the surrounding copper structure, and we're going to need to change the electric conductivity in the copper because we're working under cryogenic conditions. So it's going to be 10 to the power of 10. And then we would need to define the superconducting material, and for that we're going to define some variables first. We're going to define the power law factor and set it to 30. We're going to define the critical E field to 10 to the power of -4. We define the critical current to 100 amperes, and the cross-section area of our superconducting filaments is 3.4541 times 10 to the power of -7. And then we can compute our critical current density just by dividing IC over ASC. And finally, we're going to define our frequency to 50 Hertz. Now we can define a new material. So it's going to be our superconducting material. And the region is going to be the superconductor. We're going to select all the 5 filaments. And as properties, we're going to set the magnetic permeability to μ0 and the electric conductivity, we're going to use the power law, and using our defined expressions from before and a minimum and maximum value to not encounter any numerical issues. Having that, we can continue to the physics, and we're going to use the H5 formulation. So we're going to choose magnetism phi, transient for the airbox, and then we're going to use magnetism H, also transient, for everything but the airbox. We're going to couple those two and we're going to set our current source on the curves that are surrounding the copper. So that curve, we also see the direction, and the amplitude is going to be 80% of our critical current, and it's going to be sinusoidal with the already defined frequency. Having that, we can already continue to set up our final simulation. It's going to be transient, including both physics. For time stepping, we use the implicit Euler. Our end time is going to be 5 milliseconds and the time step 0.1 millisecond. We're going to compute it on 70 nodes, and it's going to take 1.5 hours approximately, so we just set the timeout to 2 hours. Then we'll build the mesh with the expert mesh settings using the default one here, and we're going to set the curvature enhancement to 25 to nicely capture the filaments. You can already start constructing and building the mesh. As outputs, we're going to take the magnetic flux density everywhere and the current density only in the magnetism H region, so only in our conducting region. With that, we would be finished and we can run our simulation, but with some minor changes in the script, we can speed up the convergence and get better accuracy. So first, we can reduce the order of the phi formulation from 2 to 1. And then we're going to linearize our Newton iterations for the superconducting region. So we're going to add those linearization terms. And instead of computing this integral on the whole region, we're just going to compute it on the copper. And then we're going to add another line including the linearized superconducting term. Then we need to set our tolerances to 10 to the power of -7 to get better accuracy, and we want to print out our AC losses every time step. So we're going to integrate and then print out the power losses. Now we're done with the changes in the script, and if meshing is finished, we can start to run our simulation. Also, we could use sweeps to see how the behavior for different frequencies is, if we want to check that. Now the meshing has finished. We can also show a preview of the mesh, and we can see that it captures the filaments well. And then we can start running the simulation. So now we can take a look at the results of the simulation. We can first see the printouts in the log file. So we see that for every time step we have a printout of the power losses. And then we can also take this data and compare it to the one from the paper that we reproduced in the GUI. So we can compare the losses in the superconducting layer, and we can see here in orange the ones from our simulation, and then in blue the ones from the paper, and we can see that they have a very good match. And we can also take losses in all conducting regions, so also in the copper, and we can again see a very good match.